Hi everyone, Assalamu alaikum. So today we will be talking about factor analysis. So there's two types of factor analysis. The first one is exploratory factor analysis, which we will cover in this class. And the second one is confirmatory factor analysis. We do not cover that in this class. So what we're talking about today is exploratory factor analysis. So a lot of scholars use factor analysis and principal component analysis interchangeably. Is that okay? Well, principal component analysis and factor analysis is actually two different things, but they produce similar results. So sometimes a lot of scholars use them interchangeably. So what I'm showing you today is factor analysis, all right? Okay, so factor analysis is a little bit different from the rest of your inferential statistics in the sense that factor analysis is not to test hypothesis. You do not use this to test hypothesis, okay? But rather it's a data reduction technique. For example, if you are concerned about your measurement scales, right? If you adopt your scales or adapt your scales from past research and you want to really understand whether these scales or these measurement items are really measuring the latent variable that you are measuring, okay? You want to see whether it falls or it hangs together, right? If it hangs together or not. Okay, so that's when you use factor analysis. Or sometimes you can also use factor analysis to reduce number of items so that your data is more manageable. Or if you work with smaller items, right? It's easier. It's easier to be managed, right? Factor analysis needs several assumptions. It is especially a technique that needs a large number of data. For example, Tabani and Fidel in their book in 2013 mentioned that a sample size of less than 50 or 50 and less is very poor. A sample size of 100 and less is actually poor. A sample size of 200 is considered to be fair, and more than 200 is considered to be good. Okay, so some scholars said that it is sufficient for you to have 100 to run factor analysis. It is sufficient for you to have 150 at least to run a factor analysis. You need to use this according to your own context. If you can obtain more than 150, then by all means try obtaining more than 150 and then run EFA. But if you really can't, if there's nothing else you can do and you can only get 100, then probably it's sufficient, but you need to justify using the statistician's statements that said 100 should be okay for you to run factor analysis. And then factor analysis considers factorability. This can be analyzed using by looking into the correlation matrix as well as the KMO, the Kaiser-Meyer-Olkin, and the Bartlett's test of sphericity. Your KMO must be more than 0.6. Your test of sphericity should be significant. P-value less than 0.05. As well, correlation matrix, it should be more than 0.3. We also need to take a look at the linearity as well as the outlier among cases before running factor analysis. Okay, according to Cohen's criteria, the correlation values need to be between 0.3 and 0.9 because a value of more than 0.9 indicates that actually that item is very much similar to the other item. So basically you are measuring the same thing. Why would you have a redundant item? So this is what factor analysis tells you. Okay, so let's run a factor analysis. You can use the survey data. Run an EFA on the PANA scale. So the PANA scale, the code is PN. PN1 to PN20. So let's run our factor analysis. Go to Analyze, Dimension Reduction, go to Factor. So I have already inputted all my PANAS variable from PN1 to PN20. Alright. Click on Descriptive. You want initial solution. You want coefficient, determinants, KMO and Bartlett's, as well as anti-image. Okay, and then as well for extraction, you want principal axis factoring. The default is going to be principal component, but today we will do principal axis factoring. You want to analyze the correlation matrix. You want to display the unrotated factor solution as well as scree plot. And it should be extracted based on eigenvalues. Okay, for the first example, we want to extract it based on eigenvalues. Click continue. As for rotation, we have a lot of rotation over here. Some of the rotation are orthogonal, which assumes that the factors are not correlated, and some of the rotations are oblique, which assumes that the factors are correlated. We will talk about the rotation more later on. In this example, we are using Promax. So the famous rotation method is Varimax and Promax. Alright, and sometimes you can also use direct complement. So rotated solution, continue, options. Okay, I want it to be sorted by size and surprise small coefficient, absolute value below 0.30. Continue. Okay, there you go. So my correlation matrix. For correlation matrix, you need to see whether you have more than 0.3, right? There you go. 0.3. Should be 0.3 to 0.9. So we have 0.56 here, 0.645 here, 0.810 here, 0.395 here. So everything should be more than 0.3. If you don't find correlation coefficients of more than 0.3, then you should reconsider doing factor analysis. That means your data is not good for factor analysis. And then we take a look at the KMO. So after the correlation matrix, there goes your KMO. Your KMO should be more than 0.6, right? And then your butlets should be significant. So we have no problems doing or moving forward with our factor analysis. Let's take a look. Okay, these are the KMO threshold by Kaiser. As for butlets, right? If your butlet is significant, it rules out that you have an identity matrix. So you do not have an identity matrix, you can proceed with factor analysis. If your KMO is too low, you should take a look at your anti-image. Okay, a good FA diagonal factors must be close to 1 and the off diagonal will be closer to 0, like this one here. Okay, these are your anti-image matrices. So the diagonal over here should be closer to 1. Diagonal, okay, closer to 1. And the off diagonal should be closer to 0. Right? These are the off diagonals. Where do you find this? Here. It's anti-image matrices. Okay. And then after that, so that's the extraction methods. You already saw that earlier. So extraction methods, so these are the communalities. Communalities under the extraction, it tells you how this variable over here. So don't get confused. In statistics books, when they say variables, it does not mean your independent variable, dependent variable. You have to take a look at the context. When they say variable over here, it means your measurement items. Each of your items is considered as a variable. So this explains that this variable, 45% of this variable can be explained by the retained factors. Okay, and then take a look at the total variance explained to understand how many factors do we have. So since we are looking at eigenvalues of more than 1, we will retain that factor. So these are the eigenvalues. So this is more than 0.1, more than 1, right? So we actually have 4 factors. Out of the 20 items from the PANA scale, it shows us that they load under 4 factors, right? So this is the scree plot. You have to take a look at the elbow. The higher, it shows that factor number 1 explains most of the variance. Okay, factor number 1 and 2 explains most of the variance in the 20 items, right? And then you can see there's an elbow here and then the curve is flat, right? This explains the eigenvalue. Okay, this is how you obtain scree plot. Take a look at the scree plot. And the first 4 factor together explain most of the variability in the original 18, sorry, not 18 variables, yeah, 20. Okay, then those factors are clearly a good simpler substitute for all 18 variables. Instead of having the variables load on their own, we have 20, yeah, not 18. Okay, instead of having all these variables load on their own, actually you can have 4 factors to explain them. But if you see properly, okay, over here, this looks like the elbows actually goes flat after 3. Okay, so let's take a look at the factor matrix. So this is factor matrix. This is unrotated, yeah. Okay, so let's take a look at the factor loadings. So the factor loadings is loaded under the factor matrix table. Loading values of more than 0.5 are preferable. So 4 components indicate 4 factors. 1, 2, 3, 4. Number 1, okay. PN1 17. Factor loading under component 1 is 0.665. Factor loading under component 2 is 0.479. We can say that based on the magnitude over here, PN17 belongs to factor 1. But you can't be sure unless of course you have done the factor rotation. So rotation, you can see under the pattern matrix. You see, when we compress small loadings, and when we ask SPSS to actually organize according to the highest loading to the lowest loadings, they will do everything for us automatically. So it makes your life easier, right? Okay, so this is the pattern matrix. Okay, so we have already talked about factor rotation earlier on. As you can see that Varimax is actually orthogonal. Varimax and Equamax is actually orthogonal. So they believe that there's no correlation between factors. The factors are not highly correlated with one another. Right, as for Promax, it allows factor to be correlated. Oblimit is also an oblique rotation. So this is what we call as oblique, right? So Varimax and Equamax is actually orthogonal. So, okay, so this is what's going to happen if you don't suppress small values. You see, it's really hard to read. You have to look at the numbers, all right, all of the numbers. Okay, but when we suppress smaller values, it's nicer for you to interpret. Okay, as you can see here, okay, item PN17, PN12, PN18, 13, 15 seems to load under factor 1, and the rest seems to load under factor 2, factor 3, factor 4. Okay, typically in social science, if it cross loads, we will drop that item. Okay, common practice to drop. Okay, so after we drop it, oh sorry, it's not PN16, yeah, it's PN8. Okay, PN8. So you drop it and then you run factor analysis again. Well, in theory that we know that these items here, these variables here, 20 variables, they are supposed to load under only 2 factors. So what's going to happen next is we should force them into 2 factors. That's why it's very important for you to understand your measurement scales. It's important for you to understand what you are measuring. Okay, if you don't even know that this 20 items are actually measuring several sub-dimensions, then you can't simply force it. You have to explore. Just let it explore. Alright? Okay, so this is how you report the results. These are the correct way for you to report the results. It's very important. You need to know how to use and how to report results. Alright? Okay. So these are after the results. These are reported after the force 2 factors. Alright. So this is how we force the 2-factor solution. Okay. You go to analyze. You go to dimension reduction. You go to factor. Then you go to extraction. Force number of factors 2. Because you know there's 2 factors, right? So you can have a look at the pattern matrix. You see, it's nice. It's loaded nicely. So you can see this is not loaded nicely because when I screenshotted this, I did not compress less than 0.3. I compressed less than 0.1. So that's why it shows a cross loading over here. Actually, it loaded very nicely on factor 1 and it loads very nicely on factor 2. Right, so this is a structure matrix. It tells you the correlations between the variables and the factors. Right, PN1 has a high correlation with factor number 1. So once you have all this, you can report the results. So that's all for factor analysis. In this example, you already know the factors. You know that this scale, this PANA scale, okay, this PANA scale is actually divided into 2. Positive and also negative. In a lot of other situations, you wouldn't know. Okay, for example, if you develop a scale, you wouldn't know how many factors it's going to give you. So that's why it's called exploratory factor analysis. So it's when you get to explore, for example, you have 8 items. When you get to explore, so when you take a look at the items that falls under each factors, you have to compare them and to analyze and come up with the name for that factor. Alright? So that's how you do factor analysis. Thank you very much.